Today we are going to find the derivative of e raised to power x by using the definition of the derivative. So the definition of derivative is uh, dy over dx is equal to limit h approaches 0 of f of x plus h minus f of x over h. So f of x plus h, to find this term, we simply put x plus h in place of x in our function. So our function is e raised to power x. So f of x plus h will be e raised to power x plus h minus f of x is e raised to power x divided by h. And we can write this e raised to power x plus h as e raised to power x into e raised to power h. And because if we take an example, we can write 2 raised to power 3 as 2 squared into 2 raised to power 1. So the base remains same, and the power, uh, it can be broken into two parts. So 3, which is basically the sum of these two parts, 2 and 1. So you can write this thing in this form: same base, different powers, and those powers add to give you this power and their product. So e raised to power x plus h, the power had two terms, so it can be written as the product of the same base and those two terms as powers. So e raised to power x plus h is equal to e raised to power x into e raised to power h minus e raised to power x over h. So if you look at the numerator, we can take e raised to power x common, and when we take e raised to power x common, we are left with e raised to power h minus 1 in the numerator. So now we have a product of two things. We can write this whole expression e raised to power x into e raised to power h minus 1 over h as e raised to power x into e raised to power h minus 1 over h. So we can use the property of limits to apply the limit separately on this thing and this whole thing. And to write the limit separately on this thing helps us to basically evaluate that limit very easily, because this thing doesn't have h in it, so this will remain same. So I've written the limit separately on e raised to power x and e raised to power h minus 1 over h. So as I've said, that this will remain same, so e raised to power x will remain e raised to power x. Now to find the derivative, we need to evaluate this limit. So I'm calling this equation star equation, and we will evaluate this limit and put the value of this limit in this equation to give to find the value of the derivative. So what is this limit equal to? So if we look at the if we put 0 in this expression, e raised to power 0 is 1, so 1 minus 1 is 0, so the numerator will be 0, and denominator will also be 0 because we are putting h is equal to 0. So this will be 0 by 0 form, which is an indeterminate form, and we don't know what this limit is equal to, so we need to get rid of this indeterminate form. And how can we do that? If we look at the numerator, we have e raised to power h in the numerator, and e raised to power x basically has the power form equal to this. Its power series is equal to this series 1 plus, here we don't have x, we have h, so e raised to power h will be equal to 1 plus h square over 2 factorial plus h cube over 3 factorial up to so on. So we'll put this power series in place of e raised to power h to see whether this can help us or not. So limit h approaches 0 of e raised to power h minus 1 over h is equal to limit h approaches 0, and in place of e raised to power h I am putting this power series. So this will be equal to 1 plus h square over 2 factorial plus h cube over 3 factorial up to so on. And this whole series is basically equal to e raised to power h. So we have put the value of e raised to power h, and in the end, after e raised to power h, we have negative 1 written also in the numerator. So I've written this negative 1. So this one and this negative 1 will cancel out. So we are left with h plus h square over 2 factorial plus h cube over 3 factorial up to so on. And this denominator h remains same. So when we put h is equal to 0 a few moments ago, this h in the new denominator is basically the problem, because this makes the denominator 0, and we need to get rid of it. If we and to get rid of this h, if we see the numerator, we have the terms written in the numerator have h common in all of them. So we can take h common from these terms and cancel that h with this h. So our required limit is limit h approaches 0 of e raised to power h minus 1 over h. And as I said, that we need to get rid of this h in the denominator, and that's why I've taken h common in the numerator. So when we take h common in the numerator from all the terms, we are left with 1 plus h over 2 factorial plus h square over 3 factorial up to so on. H and h cancel out. So we are left with limit h approaches 0, 1 plus h over 2 factorial plus h square over 3 factorial up to so on. And this is what we wanted. We didn't want h in the numerator, and there is no h in the numerator. We didn't want h in the denominator, and there is no h in the denominator now. All are in numerators. So we can just put h is equal to 0 in this expression to evaluate this limit. So this will become 1 plus 0 over 2 factorial plus 0 square over 3 factorial up to so on. 0 divided by anything is equal to 0. So this and all the terms coming after these two terms, because will have h in them, so all of the terms will be 0. So 1 plus 0 up to so on. So 1 plus 0 is simply 1, so the limit is equal to 1. This was our limit which we needed to find, and this is equal to 1. Now we'll just put this value in the equation, star equation, to get our result. So dy by dx is equal to e raised to power x into this limit, which is 1. So dy by dx is equal to e raised to power x. So it turns out that the derivative of e raised to power x is itself e raised to power x.